One of these pieces. So first I was going to say a few words about the midterm. I guess we didn't talk about that on Tuesday. But so the midterm was out of 80 points. There was a bonus that was worth 10. We were generally happy with the way people did on some questions, but there's some other questions that I guess people found difficult. So in preparation for the little test, make sure you really review the fundamentals of the stuff we learned, because we're not going to stop asking questions about convexity and about subgradients and that kind of stuff. That's going to kind of carry through. So maybe if we are on schedule and if we're kind of all prepared, we might even give you a practice exam for the little test, but no promises. That's what the mastery sets are supposed to be for. But so always come to office hours if you have questions, and just ask any of us if you're struggling with concepts. The mean was 52. The standard deviation was about 11. So the total score, like I said, was 80. And that was including adding up the 10-point bonus question.
And I think your union got 90 points. You solved all those questions, right?
So there's, yeah. I mean, we don't know at this point what it means to have, people ask, what does it mean to have an A on the midterm? What is a 52? Well, we don't know the answer to that question, but we're not going to obviously give everybody a low grade just because everybody got a low score. It's going to be adjusted to how most of the class did. So that was the midterm recap. Midterm recitation review was yesterday. There was very few people who showed up to that. I guess Yifei went through the solutions to the midterm, and it was a bit surprising that nobody came to that, given that people were struggling with questions. So make sure, like I said, if you don't understand things about the midterm, that you come and ask us for help, because that's how you'll gain a better understanding of some things. And so, like I said, the little test is going to be roughly the same format as the midterm. Maybe the questions will be a little shorter, and we're going to aim for about the same difficulty level. So, any questions about that kind of stuff? Okay. So how about questions in general about stuff we've covered, or just any other questions? Administrative questions about the projects or class material? Yeah. Yes, right? We'll post the midterm solutions? Yeah. We will, yeah. Okay, so today we're going to talk about dual methods in ADMM. The slides are on the web page. So for some period of time, I don't know how long, we're not going to have the projectors working, so I'm just going to start on the blackboard, but you can follow along from the slides on the web page. Put this over here. All right, so the basic setting we're looking at, right, is we're going to start with dual methods. So what's a very close cousin of a dual? It's a conjugate function. So we have some function f. In general, when we talk about conjugate functions, it does not need to be convex, but we're going to talk about optimization problems, so we're going to assume it's convex for now. So we have some function f, right? We're given f. And its conjugate this function f star, right? So how do we define it? You give it a point y, and look at all points x that are in the domain of f, and I maximize x transpose y minus f of x. Okay, so that should be pretty familiar to you by now. Right, so what's another way of writing this? Well, I can make this a min, make that a minus, and I can make this a plus, and I should have a minus out here, right? But I'll just put a minus in front of f. Right, so now this is starting to look like something we see in a Lagrangian. It's a function minus the Lagrange multiplier times x, which would have appeared in a constraint. Okay, so that's how they pop up in dual problems, right? This looks like a piece of the Lagrangian. If we're going to minimize over x, we'd get that part of the dual function. Okay, so here is this key property which you guys actually were asked on the midterm to prove this. If F is closed and convex, so who can remember what this implies actually? This was going to give us some other property with respect to conjugates. If F is closed and convex, what does that mean? Right, yeah, so that tells us that take two conjugates, I get the function back. Then if this is true, that implies this. And it also says that in this case, if I have y, that's a subgradient of f at x, then that's true if and only if. And then what comes here from the midterm?
X is subgradient of conjugate f.
Right. Okay, so again, if you didn't understand why this is true, you should definitely come to office hours or ask us about it. Basically, I'll tell you the proof in words. We just prove one direction. Okay, and one direction is fairly easy because if we look at the conjugate of f, it's written as a maximum of functions. We know what the subgradients of maxima of functions are, right? We had that rule in our notes. And they look like a union of all things that achieve the maximum of the subgradients of the guys inside. Okay, so f star was you can think of the maximum of x transpose y minus f of x. What's the subgradient of this with respect to y, the inside? If we had, I'll write it like this again. What's the subgradient of that with respect to y, of the inside? It's just x, right? Okay, and so it's the union over all x such that this achieves the max of the subgradients of the guys on the inside, and that's just x. Okay, and then there's also stuff on the outside, like you have to take the convex hull of that, we know, and also maybe the closure of that also. And that gives us the set of subgradients of f star at y. Okay, but that tells us that x is a subgradient. I mean, yeah, the points x that are subgradients of f star at y are points such that this is maximized. And when is this maximized? This is maximized if the subgradient that's with respect to x is 0. Okay, so now take a subgradient with respect to x, and what do I get up here? If I take a subgradient with respect to x up here. Y minus subgradient of f of x. That's equal to 0, right? In other words, y is in the subgradient of x. Okay, so we just proved that if x is a subgradient of f star of y, then y must be an element of the subgradient of f at x. So we just proved this direction. Okay, the other direction actually we don't even have to prove because we just use this property. I'll leave you to think about that, but we basically repeat this argument, but we stick an f star star here. Okay, and then this becomes an f star. We're going to apply this property to f star to begin with. And if f star star was f, then that just reduces to this direction. Okay, so that was kind of a proof in words, but like I said, if you're not following that, or if you have trouble understanding that, then please come in and see one of us in office hours, and we'd be happy to give more detail. And also take a look at the midterm solutions when we post them. Okay, so this is actually going to play a really fundamental role in what we do today, this property. In that, okay, so we have this conceptual connection between the conjugates and the dual, right? And so suppose we want to solve the dual. If we want to solve the dual, say, using subgradient method, then we need to take subgradients of the dual function. But what if we didn't know f in closed form, or rather f star in closed form? And this is telling us a recipe for what a subgradient of the dual function is. Right? If we wanted to derive the dual, but we didn't know what f star was analytically, we could still find subgradients of f star as long as we use this rule. This is what it's telling us. Okay, so we'll get to that precisely in just a second. But first, let's just kind of write one more if and only if, and this came from just thinking about what this is. So what does it mean for right? We said what does it mean for x to be in the subgradient of f star of y? Well, then x has to be maximizing this quantity. So x has to be an element of the argmax of x transpose y minus f of x. Okay, maybe I'll write this as, just so I don't confuse you, u, argmax over all u. Okay, and that's the same thing as saying it's the argmin, right, of minus u transpose y plus f of u. Okay, so now this should look like actually maybe a rule we can use in practice. If I want to find a subgradient of f star at a point y, even if I don't know f star, I have no idea what it is in closed form, I can still find a subgradient by solving the following minimization problem in f. Right? It may not be super efficient to do this, but it's useful if we don't know what f star is in closed form. It gives us a rule to find a subgradient. Are there any questions about that? Yeah?
It's just F conjugate, right? It's not gradient.
Here?
No, I mean this next one.
This is just f, yeah. Just f. This is a plus. This is supposed to be an f. Still confusion about that, or?
If this has the definition of the convex conjugate, but you are writing the subdifferential.
No, so the definition of the conjugate is it's the maximizer, not the argmax. Right? There's a big difference. So this is actually telling me that x is a point that minimizes this quantity. All right. So we're going to see this kind of implemented in an example. So let's suppose we have the following optimization problem. Okay, we want to minimize over all x, f of x subject to ax equals b. Okay, and we're going to look at the dual. And why we look at the dual, again, you could think maybe that was something we just were trying, or I'll give you a good reason for why we do that in a second when I change the problem slightly. Okay, so what's the dual of this? So I'm going to actually write down the dual explicitly. I'm not going to change the dual into a minimization problem or leave out constant terms. I'm going to try to write the dual just as you'd see it. So let's suppose I call the dual variable u. Right, so who can tell me what the dual is going to be here? Maybe we'll go for the Lagrangian first, and then we'll see if we can figure out the dual. So the Lagrangian is a function of x and u. Right, it's just f of x plus u transpose ax minus b. Okay. And okay, so I'll rearrange that as just f of x minus negative a transpose u transpose x minus b. Oops. Thanks, transpose u. So what's the dual problem now? What's the dual function? I need to minimize this over all x to give me the dual function, right? Okay, so, but now this b transpose u doesn't depend on x, so that's just going to appear in the dual function. So it's definitely going to have this term b transpose u. But what's this? What's that? F star of minus a transpose u. It's almost that. Yeah, it's the negative conjugate, right? Negative conjugate of f evaluated at minus A transpose u minus B plus u. Okay, so the dual problem is to maximize over all u of this function. Okay, so let's suppose we wanted to run subgradient descent on this problem. It's actually subgradient ascent, right, because it's a maximization problem. So there's no trickery here. I'm not introducing a new method. Subgradient ascent is just you take a point, initial guess, and you add the subgradient at that point repeatedly. It's the same thing as subgradient descent would do, except for maximizing the function. And you could derive that method just from thinking of maximization problem as minimizing the negative function. Okay, so we want to take a subgradient of this and add it to our guess of u over and over again. Okay, so let's call this function h. Let's call this guy h of u. So let's just do this in a couple of steps. I'm going to leave this part down here for reference. So what are subgradients of h? What does the subgradient of h look like? In terms of the subgradients of f star. Right, so I'm just using the chain rule. So I get the transpose of this matrix times subgradients of f star evaluated at minus A transpose u. But I have two negatives, so they cancel. So I just get it's A times the subgradients of f star evaluated at minus A transpose u. Okay, and so what we're going to do eventually is we're going to take a point u, and we're going to add one of these, and we're going to subtract off b, because that's the subgradient of this part. And we're going to repeat that update over and over again. That would be subgradient ascent. But let's suppose we're in a setting like we said earlier that where we don't know f star in closed form. We just don't, we can't find the conjugate in closed form. And that's not that uncommon. I mean, generically, it could be hard to derive these dual functions. We've been giving you nice examples as practice, but you probably don't know how to find the conjugate for a general function. So how would we find a subgradient of, how would we find an element of this guy? We use this, right? Okay, so first we'll try to find a subgradient of f star at minus A transpose u. So to get a subgradient of h of u, so if h at a point u, we're going to do two things, two steps. We'll first, step one, we'll solve this minimization problem. We'll find the x that minimizes over all x, right, f of x minus, it's going to be x transpose the point at which we're, maybe I'll do u again so as not to confuse you. Argument over all u of f of u minus u transpose y, but y here is A transpose. Okay, so I have too many u's. Sorry about that. We'll call this z. I've learned in my many years in the States not to say z, otherwise I get made fun of. Okay, so it's going to be plus right, z transpose A transpose u. So step one, I solve this problem, which is a problem just involving f. And u was my current guess for the dual solution. Step two, I just take as the subgradient, take as the subgradient that I'm looking for a times x. Okay, and that should give me a subgradient of h at u. Okay, but we actually wanted a subgradient of the whole criterion. So to get a subgradient of the whole criterion, I just take a times x and subtract off b. And that'll give me the subgradient of the whole criterion. So now what does, let's write an algorithm for dual ascent. Okay, so this is going to be dual ascent. So we're going to start with some guess, u0. And then we're going to repeat over and over again. Step 1, we're going to have to find this subgradient of f star evaluated at minus a transpose u0. So we're going to solve the following problem. We're going to find x at iteration k to minimize, right, the same thing here, argmin over all z of f of z plus z transpose a transpose u k minus 1. Okay, so the u from the previous iteration. Step 2, we're going to update u. Can you guys see down here? Yeah. We're going to do uk minus 1, and we're going to add a subgradient. So what's the subgradient we're going to add here? Yeah, a times xk. Is that it? Minus b. Okay, so that's dual ascent. Dual subgradient ascent. Yeah, thank you. It's a good point. So we'll have to call it, like, I don't know, tk. And that'll be our step size. And we'll choose them in the usual way. We'll do like 1 over k or something there. Okay. So what's one important special case to think of is one important special case is what happens when f star is differentiable. We're going to just think about that case for a second. In that case, it would be like dual gradient ascent. So if f star is differentiable, okay, then somehow here we shouldn't have more than one choice. Right? If we had more than one choice of xk, then that wouldn't make sense because this is going to act like the gradient in that case. So this guy kind of has to be unique. So let's actually start with the case where, let's suppose that f was strictly convex. Remember, I just erased it, but we had y is in the subgradient of f star at x if and only if x is a minimizer of f of z minus z transpose y. That was our fact we had at the start we used here. So what happens if f is strictly convex to this x here? What do we know about that x? What's that? Unique. Yeah, right. So this is unique, so I can make this an equals. Right, there's only one z here that minimizes this criterion, and that's x. Okay, so what that is telling me that right, I had this completely backwards. I probably confused a bunch of you guys, and sorry about that. Okay, so x is in the subgradient of f star at y if and only if this is true. Okay, so if f is strictly convex, then we've told ourselves there's only one x that minimizes this left-hand side. In other words, there's only one x that's in the subgradient of f star at y. So what does that mean about f star? There's only one point in its subgradient at the point y. It's differentiable, right? So therefore, f star is differentiable. Okay, so if f is strictly convex, then its conjugate is differentiable. Okay, so in that case, we get a special case of this algorithm where there's really only one point that minimizes this function here, fc plus c transpose AU. And so we're actually doing gradient ascent in the dual. Okay, so that's an important special case to think about. All right. So here's another fact that is in line with this, and I'm not going to prove it for you guys, but the proof is in the notes, and it's good practice with subgradients, so I recommend you go through it. Maybe we'll do it in recitation next week. Okay, so we just proved that if f is strictly convex, then its gradient exists. What's a little stronger than strictly convex? What's one level up the hierarchy? Strongly convex. So if f is strongly convex with parameter let's call it d. Right, so that means that the Hessian of f over all points x is lower bounded by d, d times I. Then this implies that, right, so we actually know the gradient exists already because strongly convex implies strictly convex, which implies the gradient of f star exists. But actually this implies something a little stronger. It implies that the gradient of the conjugate function of f is Lipschitz. With parameter, move this out of the way. With parameter d. What's that?
Is it d or 1 over d?
1 over d. Yeah, thank you. Okay, so you're probably right, but the proof I have in the notes is only one direction. But I think you're right. Okay, so let's think about this fact for a second. Is this a favorable property or an unfavorable property when we're thinking about how fast this converges? Right, so what do we need to say that this converges? Suppose we're looking at the gradient version of this. What's our standard condition to say that it converges on the function we're minimizing, which in this case, right, this is dual ascent to minimize f star, right, or that function over there that involves f star. We need f star to have a Lipschitz gradient, right? And then it converges with rate 1 over epsilon. That was like our standard gradient descent convergence rate. Okay, and so we know how to choose t. We choose t to be, if we knew the Lipschitz constant, we'd choose it to be less than or equal to 1 over Lipschitz constant or less than or equal to d. So if we assume that our function is strongly convex, then we can perform dual gradient ascent, and it converges at the rate 1 over epsilon. Is that kind of a favorable and unfavorable conclusion to draw? What if we did it in the primal? What if we didn't even go to the dual and f was strongly convex and we applied gradient descent? What happened when a function was strongly convex and we applied gradient descent? What's that?
You would get 9 over epsilon.
Yeah, right. Log of 1 over epsilon. So it would be what we call linear convergence, right? Not just.
Strong convexity and Lipschitz together in order
it's strongly convex and not differentiable, then you still get 1 by t.
But if its sublevel sets are bounded, then it's strongly convex. Strong convexity implies that it's Lipschitz. It's gradient Lipschitz. So they pretty much always occur together. So if we're doing a minimization over a function whose sublevel sets are bounded because we chose a good initial point, then essentially it's the same condition.
So if f is not differentiable, then you get a 1 by t raised to
Yeah, I mean this is probably a detail we don't need to stress too much on because, I mean, right, if we're minimizing a function who is a bounded sublevel set, which is typically all that we do, then if we know that its Hessian is bounded below, then it's also bounded above.
No, but I'm saying it needs to be differentiable in the first place. So you come across, I come across problems in which you're minimizing like a margin with a regularization term, and it's strongly convex because you have an L2 square regularization term, but it's not differentiable. So it's actually strongly convex, but the best you can do is 1 by t. So, I think that problem arises quite naturally.
Okay, so that's a fair point. Okay, so we'll just say that if it's strongly convex and it has a Lipschitz gradient, okay, then in the primal we get what we call a linear rate of convergence, but it's very fast, right? Here, if we assume strong convexity of f, and we try to apply dual gradient ascent, we get a convergence rate, but in practical performance, that's way below what we kind of consider the appropriate speed given the strength of our assumption.
So I think basically now in your primal, if f is differentiable with the Lipschitz gradient, then that implies that f star is strongly convex. Right? So if you're assuming f is strongly convex and its gradient is Lipschitz, then f star is also strongly convex and its gradient is Lipschitz, because the appropriate property implies the other opposite, and then you'll get the stronger rate for the other one also. So you actually, I don't think you lose. And if you don't assume it's differentiable there, then you get 1 by t, and it's not strongly convex here, so you get 1 by t. So that also matches. So I think that they're going to do the same thing.
So it seems that's a good point. But the standard kind of practical performance is that doing dual subgradient ascent or dual gradient ascent kind of is a lot slower than what you do in the primal, right? So what we're going to get to this point is that one of the reasons we don't use this is because of its kind of the fact that it does not converge quickly. So maybe we have to iron out the details. I mean, that sounds correct, assuming that f star star is f, right? But maybe we need better motivation for that. Okay, so this is a fact that you can remember. Maybe the takeaway point that I'm trying to make is that number one, this algorithm practically is not fast, even if f has nice properties in many cases. But another property that's important that has to do nothing to do with speed is that here we're going to end up showing that we get convergence in the dual criterion value, right? That's what we typically assume, right? That's what we typically prove when we prove rates about these algorithms. But it actually takes a lot stronger conditions to prove that we get a primal solution. So it's not trivial at all when we run dual gradient ascent or dual subgradient ascent to actually get a primal solution that is feasible. So to prove that that comes out of your algorithm requires a lot of extra assumptions. Okay, so that's one of the biggest drawbacks besides the fact that it's slow, is that we could end up at the end of the day with a primal point that's actually infeasible, right? Because there's no reason to think that it actually would have u being equal to ax minus b. And also, we don't really know, except under very strong conditions, that it's actually optimal, that point x. Okay, if that was a solution we're trying to find in the first place. Okay, but we like this method, though. And why do we like it? Well, it's for the following reason. This is a term that you'll get heard thrown around a lot. It's dual decomposition. Okay, so let's suppose I have this problem now. Instead of minimizing just f of x, I'm going to minimize the sum of fi of xi. So I can think of xi as just indexing a block of the optimization variable x. Okay, but now I have this constraint subject to ax equals b again. Okay, so this looks like it almost decomposes into, let's suppose we have b blocks, b different minimization problems, right? But this constraint kind of complicates it. It brings all the optimization parameters together. What happens in the dual we're going to see is that the problem decomposes. So that's the kind of the magic of dual decomposition. So the Lagrangian as a function of x and u, right? It's just the sum of fi xi minus, again, it's just going to be plus u transpose a transpose x minus b. Okay, now I'm going to write this in a certain way. I'll take A, and I'm going to carve up the columns of A corresponding to how I divided that vector x. So I'll carve it up into A1 through AB. And I'm going to write x as, right, x1 through xb. So this is just A times x. Right? And another way of writing that is just, this is just the sum of AI xi. Okay, so what happens to this term in the Lagrangian? It becomes u transpose the sum of AI xi minus b. And then I'll just collect all the xi terms. I get the sum of fi xi minus, I'll do the same thing as what we did in the other problem. It's just u transpose, or rather I'll write it as minus a transpose u transpose xi. And I still have minus b transpose u. Thanks. Okay, so then what's the dual? The dual, if this is the primal, the dual is going to be to maximize over all variables, dual variables, right, u, of the minimized thing over x. So what happens when I minimize this over x? It's the same calculation as before. Yeah, I can just take, I can minimize over each component of x separately, right, each block. So I get minus the sum of fi star evaluated at minus ai transpose u minus b transpose u. Okay, so again, maybe this doesn't look like it decomposes just yet, right? Because how can I write this as a bunch of different minimization problems? But let's apply dual subgradient ascent to this. Okay, so what would the steps to dual subgradient ascent be? Suppose I've already chosen initial point u. Then the first thing I have to do is I have to find a subgradient of this. Here's the key. What are subgradients of this function? Well, it means I have to find a subgradient of this sum, and I subtract off b. Right, but a subgradient of the sum is just a sum of the subgradients. So it means I need to find a subgradient of this for each I. So how do I do that? That means that for each I, for every I going from 1 to b, I find xi, which is an element of the argmin of fi evaluated at minus a transpose, evaluated at xi argmin over all z plus z transpose ai transpose u. And then I'm just going to, so I'll call this xi k. right? And this would have been u k minus 1. And then the second step is I take this and I add it to u. Right, so I take uk minus 1 plus a step size times subgradients of the criterion. So what's a subgradient of the criterion now after I found x, I, k? It's going to be a sum, right? Because I found a subgradient of each of these terms individually. So the subgradient is the sum of the subgradients. And I have to do the same thing as before. ai, xi, k. And then I have the b integrating as well. Right, so okay, so that's subgradient ascent for this problem. And here's the really key part is that now this part has decomposed into b separate minimization problems. Right? To find subgradient, I just do these separately or in parallel. And so I have this picture in the notes. I'm not a very good artist, so I'll try to recreate it on the board. But here's the schematic, right? So we have, let's suppose, this central hub, right? This guy's going to collect information, and at any iteration, he's going to have uk minus 1, and he's going to send to a bunch of different nodes. He's going to send just uk minus 1, our guess for the dual variable at the last iteration. And each one of these nodes, they're going to have with them AI. That's all they need to store, is that chunk of the matrix, right, corresponding to that block. And each one of these nodes, they solve a problem that looks like min fi of xi plus z transpose ai transpose uk minus 1. And then they send back to the central node that minimizer, xik. Right, so they each send back their value of that chunk of the primal variable that they're guessing. And then at the center, this guy just compiles all the information, and he updates u according to, right, uk is uk minus 1 plus that stuff, where he's collected all the xi's. Okay, so this is a nice way to be able to solve this problem in parallel, even though it didn't look like initially we could do that because of this constraint. Questions about that? No? All right, so the same thing works with inequality constraints. We didn't need an inequality constraint here. We could have had inequality constraints, so it would have worked just fine. Won't go through that. Yeah?
Read that step where we converted to the conjugate and then like unconverted to the conjugate.
Where? I didn't quite understand the question, sorry.
Right, so where we write max u and then f star, seems like you just like eliminate that line, right?
Yeah. Oh, yeah. I mean, the algorithm doesn't need this form, but this is what I can think of this as an algorithm for solving this problem, but we just were using this to drive the dual criterion so that we could see this is just doing subgradient ascent on this problem. Okay, but the thing to remember, I guess, Adi made a very good point about kind of the convergence rates we need to prove properties, but maybe an important thing to remember is that it's not immediate that if we solve this problem, we get a primal solution that's feasible. Okay, that's really the main drawback. The big advantage is that we get decomposability, so we can solve bigger problems because we send it across chunks. So one kind of drawback to keep in mind is that practically it's not very fast. And the second drawback is that we don't necessarily get an x that satisfies this, or the inequality constraints, even at convergence, unless we assume a lot more about the problem. Yeah?
Can you give more of an insight of why that's true? Because if we're doing gradient descent at the opposite normal, the gradient will be 0. If the gradient is 0, then AX is equal to B. So like, why do we not get feasibility?
The gradient is 0. Oh, you mean in the dual the gradient is 0?
Yes.
Right, so we have subgradients in the dual generally.
Right, but the subgradients are AX minus B for a certain X that we get in step 1.
Mm-hmm.
So at convergence, that should be 0 or very close to 0, right?
Mm-hmm.
And if that was the case, then AX would be equal to B, so we would get feasibility.
So yeah, I think that the problem is exchanging a limit and a subgradient in the mathematical argument. Right, so we're saying that in the limit the subgradient is 0, but that's saying that there's feasibility. It's saying it's kind of putting the subgradient on the outside and the limit on the inside. Because we really want to know that the limit at the limit we get AX minus B equals 0. So there's this condition that we have to kind of know to exchange the subgradient and the limit. I mean, just practically speaking, you can think that we don't often stop the algorithm. Well, we never stop the algorithm in practice when the gradient is 0, right? We always stop when it's small. And in that case, in terms of feasibility, it's either all or none, right? Being close to feasible, if AX is kind of close to B, then that might be good for some applications, but it might be bad. Maybe we need a strictly feasible point. Right? We can't have AX being a little bit bigger than B. That could even be a bad thing, depending on what the application is for.
The stopping point, just simply a projection, do a simple projection of the solution to the feasible set, because it actually gives you a good approximation.
Yeah, good point. It could give you a good approximation, right? Especially because you know that, like Otto was saying, that at that point the subgradient is very small. So the distance to the feasible set is very small. But we're gonna talk about an algorithm that basically improves upon this in one way, and then we're going to talk about a third algorithm that kind of is the saving grace. So we'll get to other ways to fix this problem. We don't need to do projection after the fact. Okay, so what we're going to talk about next is, so by the way, there's an example in the notes that gives kind of this nice price coordination interpretation of this algorithm. And since I'm lecturing on the blackboard, I'm going very slow, so I can't cover it. But you can interpret these steps in a kind of very sensible way if you are willing to believe kind of this interpretation that comes from, I'm not sure, like an economic standpoint. Okay, there's a explanation for what the dual variables are doing and for what these residuals mean. So take a look at that slide. So we're going to use something called the Augmented Lagrangian, and it's going to look like basically we did nothing. So we're just going to take this problem, and we're going to pull one of our tricks that now seems somewhat common in this course. Well, not this trick, but the fact that we're doing tricks seems common, I guess. So we're going to take this, and we're going to write this problem in this form. We're just going to add to it plus rho over 2 times the norm of AX minus B squared. So did this change the problem at all? It didn't do anything, right? Because AX was equal to B at the solution. That's nothing. No matter how big rho is, there's no contribution to that term. But minimizing this problem is the same as minimizing that problem. Okay, so why do we do this? Well, there's two reasons. The first is that practically, I guess at this point it's debatable whether or not theoretically it improves convergence, but practically it helps speed up the convergence of the corresponding dual subgradient or dual gradient descent approach now to this problem. Because this is always strongly convex, no matter what f was. Because I have this this rho over 2 term. I suppose here I also want to know that A is full column rank for it to be strongly convex. But practically it speeds up the convergence of the algorithm. And the second important reason is that this provides a venue for getting convergence in the primal solution under weaker conditions. So we're not going to go into details, but this is called the method of the augmented Lagrangian. So why do we call it that? Well, it's because the Lagrangian is just what it was before, right? It's just L of xu. It's what it was before. And then we just have this additional term. So you can think about it as augmenting Lagrangian or as augmenting the criterion of the primal problem. It's the same thing. Okay, so the good news is that, right, we get better convergence, better speed. And actually, there's also a natural choice of the augmented Lagrangian, of the step size in this case. We can actually just choose rho as the step size. Okay, and take a look at the notes to see the formal reason for why that's true. But it has to do with the stationarity condition. So another advantage, we don't need to choose step sizes. We always just choose rho there. So what's the main drawback of this? What's the main drawback of adding that ax minus b term? So think about carrying that through to here. Right? All that did was here we just wrote plus, actually, and I can't even really write in this form, so I've already kind of told you the drawback implicitly. But I would have to add an ax minus b norm squared when I'm finding the subgradients. So what did that mess up? Yeah, it's not parallelizable, right? So I'd have to find x1 through xb to minimize the sum of fi xi plus b transpose ai transpose u. And if this was my original, same as my original problem, and this decomposed nicely, right, across all I. But now I have this, sorry, let me put z here, zi ai transpose u. So if I just take an argument overall, z1 through zb, that's the same thing as doing each of these arguments separately like we had over there. But now for this problem, it's not just fi, the sum of fi is the criterion, it's plus the sum of az minus b squared. Right, rho over 2 times that. So I've messed it up. I can no longer decompose this into b separate minimization problems. Okay, so advantage, much better convergence properties, practically speaking. And disadvantage, we've lost decomposability. All right, so there's a saving grace that's going to give for us the good convergence properties of the augmented Lagrangian problem, but with the decomposability of the regular dual decomposition. And that algorithm is called ADMM. And it's actually quite an old algorithm. It's about as old as either of these two algorithms are. But it just kind of recently gained a lot of attention when there was this very nice kind of review paper written about it that revived interest in ADMM among people who do optimization problems in machine learning and statistics. And it was written by the author of your textbook. He was one of the authors of this paper. Okay, so what do we do? We augment the Lagrangian just like before. And so now we're going to do something, fairly natural, I guess, from the perspective of just the intuitions behind this method. So I'm just going to write this actually in terms of two variables, a1 x1 plus a2 x2 equals b. So I'll just write this as the sum of the minimum of those two things. Okay, so what do I do? I'll form the Lagrangian just like before, L of x1, x2, and u. And that's just equal to f of f1 x1 plus f2 x2 plus u transpose a1 x1 plus a2 x2 minus b, and then plus this guy, right? a1 x1 plus a2 x2 minus b squared. And so what would the usual dual subgradient ascent do, or dual gradient ascent, is that we actually minimize this over, we form a dual by minimizing this over x1 and x2, and then we take gradients of that, and then we had this rule, right, which said that that corresponded to, well, I erased part of it, but solving these problems, but I had the complication that I had that ax minus b squared term still in there. So what ADMM does is actually, it stops short of deriving the dual, and it doesn't really take conjugates of the dual, subgradients of the dual function, but it chooses the points x just to minimize the Lagrangian directly when I plug in my dual estimate. So ADMM is I start with u0 and I repeat the following steps. The first step is that I choose x1, okay, to be an argmin over all points x1 of the Lagrangian evaluated at x1, x2, my previous guess at x2, so x2 is fixed, and my previous guess at u. Okay, and the second step is I'm going to take x2 to minimize the Lagrangian when I evaluate it at a fixed point x1, actually the one I just solved for in the previous iteration. It's not x1k minus 1, but x1k, and x2 in my dual variable. And then this third step is going to be the same as our dual subgradient or dual gradient update. So we take u from the previous iteration, and we add to it step size times the subgradient. And the step size, like I said, is just going to be rho. No need for choice of step size. And it's just a1 x1 k minus or plus a2 x2 k minus b. Okay, so that's ADMM. Stands for alternating direction method of multipliers. Okay, so another word for the dual decomposition is method of multipliers. And here we're doing alternating direction method of multipliers because we're not actually solving for x1 and x2 jointly like we would have had to had we done the usual dual ascent. We're doing them in alternating directions. First x1, then x2. So in other words, if I had done the usual method of multipliers, the usual dual gradient ascent to this problem, I would have had to done the following problem. Minimize over just this first step over all x1, x2 jointly. Take that, call that x1k, x2k, proceed to the third step. But because I'm doing this modified method, I'm able to do them separately. Yeah? If I do this first? Different algorithm, actually. So that's one of the things about ADMM is that it's not going to give you the same answer after a certain number of iterations. It'll have the same properties. It's not going to have theoretically any different properties, but it'll be a different algorithm in what order I choose to update those. Another important distinction, what happens if I put xk minus 1 here? Right, maybe that's important because if I'm actually thinking about like I'm doing this right in true parallel, then I would put an xk minus 1 there. This does not necessarily have the same convergence properties as the algorithm does when it has xk. Okay, so in order to get a truly parallel algorithm out of this, we have to be more careful. This is useful because it chunks up the problems into smaller subproblems. So at least we're actually solving smaller subproblems.
I think using the k minus 1 there gives you also gives you some convergence property, but weaker. But the advantage is that we can generalize this x1, x2 to more than 2 blocks.
Yeah. What if I put a k minus 1 in there, you're saying?
Yes.
Yeah. Yeah. So if you look at the review paper by the author of your textbook, Steve Boyd, and others, they talk about parallelizing computations for a bunch of problems, and they talk about these issues in detail. And that's the general impression I got, is that yeah, it's not going to be by the same standards that you achieve convergence, but there are cases in which you do with a little bit stronger assumptions. Yeah.
So the x1 and x2 are still block variables. The augmented term is still not decomposable.
Right.
What is this phi over the previous method?
Oh, well, so this is decomposable. That's the thing. I mean, the previous method would have forced us, because of the non-decomposability, to do this argument jointly over x1 and x2. So here we've foregone like literally taking subgradients of the dual function. We've just said let's just minimize the Lagrangian blockwise, once over x1, once over x2. So this is not a literal translation of dual gradient ascent written in this form. It's something different, but it has the good convergence properties of dual gradient descent, and it has the decomposability of the method of multipliers. Yeah.
So if you randomly choose like x1, x2, which one goes first? Still have the same convergence property?
That I don't know. So the question was if I had at every step whether I randomize whether I'm choosing x1, x2, what are the same convergence properties. So we'll talk about coordinate descent in the next lecture maybe. And so for that, it looks similar. We minimize over blocks. And yes, it's true. Any permutation I take at any step will give me the same convergence properties. For this, I'm not sure, actually. Does anybody know? Do you know? No? All right, so I'm going to skip over the convergence guarantees. You guys can look at the slides, but let's say they're stronger.
Sounds like that might be something useful for like parallelization, and meaning sometimes if you're doing something asynchronously and one happens to go first before the other, and in another round maybe something else has to go first before the other, but they're not synchronizing, and like you might be something useful to check for.
Yeah. Yeah, but if you're doing it in parallel, then you wouldn't have a k here anyways, right? You'd probably have.
Like, the same shared memory,
I
but
see.
Different processors accessing the shared memory. So in one case, one might go first and update the shared memory, and then the other might access it.
Yeah.
But it's not parallel, but it's shared memory.
Yeah, it's true. I guess it could be a useful thing to know. So I'm going to quickly go through and just one example of what we can do with ADMM, and then we'll call it quitting time. So first, a couple practicalities. It's not generally known how this converges in terms of a rate. People have shown that for certain special cases, like if my f is like smooth thing plus an L1 penalty, if that happens to be my f, then it has certain rates. It has basically the convergence rates of first order methods under the same conditions. Okay, but in general, it's not known. If you tell me that I have an f that has very generic properties, it's not really known how this converges. There's actively people kind of who are researching this problem in the literature right now. But the consensus is that practically it tends to behave like a first order method. So if you want, generally speaking, it's not always true, but if you want a solution to very high accuracy with ADMM, you have to run it for many iterations. So I have to repeat these steps many, many times. But if I just want a solution that's a coarse approximation to whatever the true optimization solution is, then I can get a good one in a handful of iterations. Okay, so we also would not choose to implement this method unless these two steps were fast. Right, if these were hard minimization problems, then we wouldn't choose ADMM. It just wouldn't make sense. So the trick is to figure out, well, we'll see one example, how to carve a problem into an ADMM form such that these are kind of fast steps. Okay, but to do that I have to just introduce one quick thing that's called scaled form. So for scaled form, I just basically change the dual variable by taking, I just take a different scaling of the dual variable u. I call it w, which is u over rho, this augmented Lagrangian parameter. Okay, and then it just tends to be easier to write these steps. That's all that happens. So the first step I can write as x1 k is the argmin over all x1 of f1 of x1 plus rho over 2 a1 x1 plus a2 x2 to the k minus b plus w k minus 1. That's supposed to be k minus 1 squared. Okay, so it's a little easier way of writing these steps. And the fact that they're equivalent is very straightforward. It's just you basically plug in everywhere you see u, you multiply by rho and you divide by rho, and then you call that rho times w. Okay, the next two is just the same thing, right, but we're going to minimize over x2 and plug in our value of x1 to the k. Then the dual update step looks like wk minus 1. And then I don't have to multiply by anything here. I just I do a1 x1 to the k plus a2 x2 k minus b. That's a little easier form to remember. Okay, so we just take the augmented Lagrangian, which is the residual of the constraint, right? This is a linear quality constraint plus the new, is it a minus? Oh. Yeah, right, this squared, thank you. Plus w at the k minus first iteration. Okay, so here's one example of one problem you can solve with this. It's the generalized lasso problem. So remember we had this pretty lengthy discussion last time about how we might solve a generalized lasso problem. We talked about like different forms of the criterion function and how we might choose to use primal dual interior point method, how we might choose to use generalized gradient in the primal or the dual, etc. Here's another way to solve the problem. Let's use ADMM. So it's going to be somewhat of a more special case where we have least squares loss. But you could think about what happens when this loss is not least squares as well. So this is our problem. Okay, we want to minimize this overall beta. So how do we apply ADMM to this problem? It's the same kind of puzzle we have when we encounter a dual, that there's no linear equality constraint. So what do? I do something just like I do with duals. I introduce a variable. I'll just call it z, and I'll write subjects to db minus c equals 0. And I'll put a z in there, otherwise that would have done nothing. Okay, so now we're just going to look at that, and we're going to write down an ADMM algorithm. It's going to take us no time at all. Right, so this is going to be F1, that's going to be F2, and that's our linear equality constraint. Right, so what's the first step? We're going to choose beta to be the minimum over all beta of this plus a square term involving this plus w. Right, so it's y minus x beta squared plus rho over 2. I can't if I missed a constant here. Yeah, that's right. Rho over 2 dB minus z plus w squared. Okay, so if we had more time, we could see that just by differentiating this criterion, we get an exact closed form solution, and that tells us that beta is going to be x transpose x plus rho d transpose d. I'll write inverse, right? But in general, if that's not invertible, I have to use the pseudo inverse times what's the just x transpose y? No, we have x transpose y, right? Plus rho times d transpose z minus w. Okay, that's our first step. Solve that linear system. Second step is going to be to minimize this plus this this term with y minus x beta in there as well, right? But minimizing over z, that doesn't matter. So what do we get when we do this this step? Minimize this plus this over z. Soft threshold, right? It's just the prox function of the L1 norm, right? Because my optimization variable is z, so this is a constant, and it's like squared error plus L1 norm. So it's z gets soft threshold at what level? It's actually going to be at the level lambda over rho. So I'll just divide by rho to get it in a more familiar form, and then the value which we're evaluating the prox function is going to be dB minus w. Okay? And then the third step is that we're just going to take w and we're going to add something to it. Okay, I'm not going to write it down. It's just the residual. So that's an algorithm for the generalized lasso. Right? It was much faster to derive this than it took us to derive a dual and look at primal dual interior point method. And you could imagine programming this in MATLAB or in R, like it'd take you maybe 5 minutes to get this working. So very simple to get this to work. When would we use this? When would we ever use this for the generalized lasso? Well, we use it when, again, we probably don't want an incredibly accurate solution because ADMM takes a long time to converge to high accuracy. We'd also use it when these steps are fast. So when is it the case that these steps are fast? This step is always fast, right? Soft thresholding always takes linear time, or just exactly n time if this is n variables, or 3n time if you're doing that many checks. How about this step? When is this step fast? Yeah, so if both x and d had structure, or they are both sparse and not structured, then we could solve this fast. Okay, even if I had a pseudo-inverse there, that's generally true as well. So if I have large sparse X matrix, large sparse D matrix, then I can do this step very fast. Okay, so that really covers a lot of the problems we talked about in that lecture, whatever it was, a week ago from today. If this step was, if X and D were both dense, then this is not a good idea, probably, right? Because this is like if X was n by p, this would be like about p cubed operations. Okay, one thing I could do if X was dense was that I could maybe compute a matrix factorization of this matrix at the beginning, like a QR or a Cholesky or something. And then after I compute that, which costs also p cubed operations, solving this in each iteration is only p squared. That's still pretty costly. So we would probably avoid it for large problems in which one or both of these is dense. Any questions?
Since this is fixed
Yeah, but so there's two, like I said, there's kind of two things. The first is that even if it's a one-time cost to compute a matrix factorization, then it's still squared every time we want to apply it, right? If I compute a Cholesky, okay, but that's fairly expensive. The second actual reason is that, one, I didn't get to go into detail, is that often choosing rho is a very finicky business. So rho really affects the convergence of the algorithm. We know that for any fixed rho, it's going to converge. But choosing rho really affects the convergence in practice. So often what's the best strategy is to update rho at every iteration. And there's recipes to do that explicitly in that paper I mentioned, which is referenced in the notes. And if we do that at each iteration, then we can't just compute one matrix factorization. That's a really good point, right? So I never talked about this. This is a kind of, it's a parameter that's frustrating to deal with because statistically it has no relevance. Any value of rhos should give me the same answer. But from the optimization perspective, it really affects the convergence of the algorithm. Okay, that I guess is the end of our lecture. Hopefully we'll have the projectors working on next week.